There is a place in the universe where the laws of physics break down, where space itself is torn open, where time slows and then stops. Nothing that enters ever returns. Not light, not information, not time. We call it a black hole, and for most of human history, we thought it was nothing more than an equation, a mathematical curiosity, something the universe probably wouldn't bother with. We were wrong. At its core, a black hole is a region of space where gravity has become so extreme that escape is impossible. The boundary of that region has a name, the event horizon. Cross it, and you are gone. Not destroyed, not immediately, but lost. Separated from the rest of the universe forever. Einstein's general theory of relativity predicted this in 1915. He described gravity not as a force, but as a curvature in the fabric of space-time itself. Massive objects bend that fabric, and if an object is massive enough, dense enough, it bends it into a point of infinite curvature. That point is called a singularity. We don't fully understand what happens there. Our physics, every equation we have, breaks down at the singularity. It is, in the truest sense, the edge of what we know. Most black holes begin as stars, not ordinary stars, but giants. Stars 20, 30, 50 times the mass of our Sun, burning through hydrogen at a ferocious rate, radiating enough energy to outshine entire galaxies. For millions of years, these stars exist in a state of tension. The energy released by nuclear fusion pushes outward. Gravity pulls inward. They are balanced, barely. But fusion cannot last forever. When the fuel runs out, the outward pressure vanishes, and gravity wins. In a fraction of a second, the core collapses. The outer layers rebound in one of the most violent events the universe produces, a supernova. An explosion so bright it can outshine an entire galaxy for weeks. What remains at the center, if the original star was massive enough, is a black hole. A point of infinite density, wrapped in an event horizon. Silent, invisible, permanent. Not all black holes are equal. The ones formed from dying stars are called stellar black holes. They typically range from 5 to several tens of times the mass of our Sun. Compact, dark, and scattered throughout every galaxy in the observable universe. Then there are the supermassive black holes. These are the monsters at the hearts of galaxies. Millions, sometimes billions, of solar masses compressed into a region smaller than our solar system. How they formed is still one of the great open questions in astrophysics. They may have grown slowly over billions of years, consuming gas and merging with other black holes. Or they may have formed from the direct collapse of enormous primordial gas clouds in the early universe. We don't yet know. And then there is a third category, theoretical but compelling: primordial black holes, possibly formed in the first fractions of a second after the Big Bang, before any stars existed. Some physicists have proposed they could account for a portion of dark matter, the invisible substance that makes up most of the mass in the universe. We have not confirmed their existence, but we have not ruled it out. Imagine you are falling toward a black hole. From a distance, you would see something extraordinary. The intense gravity bends light from behind the black hole, wrapping the entire visible universe into a ring around it. Every star, every galaxy, compressed into a halo of light. As you approach the event horizon, an observer watching from far away would see something strange. You would appear to slow down. Your image would redden, dim, and freeze, suspended at the boundary, never crossing, never arriving. This is gravitational time dilation. Near extreme gravity, time itself runs slower. From your perspective, you would cross the event horizon in moments. From the outside universe, you would appear to hang there forever. But the journey would not be comfortable. As you fell closer, the difference in gravitational pull between your head and your feet would become enormous. You would be stretched lengthwise and compressed from the sides. Physicists call this spaghettification. It is exactly what it sounds like. For a stellar black hole, this process would begin before you even reach the event horizon. For a supermassive black hole, millions of times more massive, the tidal forces at the event horizon are gentler. You might cross it without immediately knowing. And then the singularity awaits. What happens there, we cannot say. Our mathematics produces infinities. and infinities in physics are usually a sign that our understanding has reached its limit. At the center of our own galaxy, approximately 26,000 light-years from Earth, lies Sagittarius A star. For decades, astronomers tracked stars near the galactic core moving at extraordinary speeds, whipping around an invisible point in tight, fast orbits. The mathematics allowed only one conclusion: something containing 4 million solar masses was hiding there. In 2022, the Event Horizon Telescope collaboration released the first image of it: a glowing ring of superheated gas, a shadow at its center, our black hole. It was not the first image of its kind. In 2019, the same collaboration had captured an image of M87 star, the supermassive black hole at the center of the Messier 87 galaxy, 55 million light-years away, 6.5 billion solar masses. A jet of plasma shooting from its poles, stretching 5,000 light-years into space. 2 images, 2 black holes, both confirming what general relativity had predicted over a century earlier. Einstein, it turns out, was right. There are an estimated 40 million stellar black holes in the Milky Way alone. At the center of nearly every large galaxy, a supermassive one. The universe is riddled with them. These are not anomalies. They are not exceptions. They are fundamental. Black holes force us to confront something uncomfortable. That our best theories of the universe are incomplete. That at the singularity, where gravity and quantum mechanics should meet, they do not. The two great frameworks of modern physics, general relativity and quantum theory, cannot both be right at that point. Something deeper is waiting to be discovered. We have imaged black holes. We have heard them collide, their gravitational waves rippling across 1 billion light-years to vibrate our instruments by less than the width of a proton. We have mapped their influence on the galaxies they anchor, and yet the singularity remains beyond reach, beyond understanding. Perhaps that is fitting. The universe keeps its deepest secret inside the one place from which nothing, not even light, can escape.